what is the moment of inertia of a sphere rotated about an axis through its center? Yeah, okay, I know the answer. Let's go ahead and put down the answer. I is 2/5 mr squared. So if that's what you want from the video, then done. That's it. Of course, you could have looked that up. No one really cares about that. Well, you want to know how you get that number. And I'm going to go through all the gory details of finding the moment of inertia for this object rotated about its center. And bonus at the end, I'm going to do a Monte Carlo calculation for fun on Python, but you don't need that. So what is the moment of inertia? If I have a rotation of a rigid object about a fixed axis, then the moment of inertia describes its rotational properties. Yeah, that's a good way of pointing it. And if I have a finite elements on here, it's just the sum of each mass times its distance from the axis of rotation, that distance squared, and I add them all up. Of course, if I have a solid continuous object, then I need to turn that summation into a volume integral. And so that volume integral is going to be r squared dm. Now, let's be careful here. Remember, I'm actually going to call this r prime, because it's the distance from the axis of rotation, not the spherical coordinate r. Those are different things. Okay, so yes, if I want to integrate over the volume of a sphere, I should probably use spherical coordinates. So just to remember spherical coordinates, we describe the position of an object with the distance from the origin r, the angle from the z-axis theta, and then the projection down into the xy plane of phi. And if I do that, my volume element, remember in Cartesian coordinates, the volume element is dx, dy, dz, very nice and easy. In spherical, it's r squared sine theta, d theta, d phi, dr. And this looks a lot easier, but the problem with Cartesian coordinates is your limits of integration are all messed up, right? Because how do I add up this way? They all change. Whereas I can get easy limits of integration in spherical coordinates. I'm going to have r goes from 0, actually let's put it like this. R goes from 0 to r, the radius of the capital R, the radius of the thing. Theta is going to go from 0 to pi, because we're going to go from here all the way down here. And then phi is going to go from 0 to 2 pi. So it's going to go all the way around the circle. Okay, so the first thing I need to do is get to, and this isn't too bad, to get dm in terms of dv, right? Because I don't really care about dv, I care about the mass element. So if I have a constant density, rho is mass over volume, then that's also going to be equal to dm over dv. So dm is going to be rho, the density, times dv. And let's just go ahead and put this here. Rho is going to be the total mass divided by the total volume, 4/3 pi r cubed. And we'll get back to that later. But right now, let's just use that for dm. So if I put all that together, I can turn my integral into this. It's going to get a little messy, so just hold on to your pants a little bit, or whatever you like to hold on for support. So I'm going to say I is the integral, and the order of this doesn't matter too much right now. We can fix it later. R equals 0 to r, theta equals 0 to pi, phi equals 0 to 2 pi, and then I have rho, and then I have my volume element for the dm, which is going to be r squared sine theta. See, I already said it's going to be messy. Sine theta, d phi, dr, and then I have to do, that whole thing is dm. And then I have to do, that r is r. And I'm going to say r prime squared. That's it. So it's r squared dm. And that r prime is going to be actually, so here's my, so this is r, that's r prime. And so that angle is theta, so r prime is going to be equal to r sine theta. So that means I'm actually going to get this. Let's just put this as 3 integrals. I'll put the rho out front. Now I'm going to get r squared sine theta times r squared sine squared theta. So I'm going to get r to the 4th sine cubed theta d theta d phi dr. That's what I need to integrate, and that's what we're going to do. Now, where should we start? We should start with the easiest thing. Let's integrate d phi. Let's do the phi integral. Since there's no phi's in here, the integral of d phi is just phi. So this is going to be equal to rho times the double integral of, let's just put r and theta, and this is going to be r to the fourth sine cubed theta d theta dr phi from 0 to 2 pi. And so if I evaluate that at 2 pi, I get 2 pi, 0, 0. So this just brings the 2 pi out front. So now I have I equals 2 pi rho, that's a rho, r theta, r to the fourth sine cubed theta dr d theta. How's that look? Okay, let's do the theta integral next. And so you may say, okay, it's sine cubed theta d theta. If I integrate that, I get sine to the fourth. So maybe that's sine to the fourth theta evaluated from theta equals 0 to pi. And it's not, over 4. No, it's still not. It's not that, right? Because the integral of sine theta is negative cosine theta. So you can't just say, oh, it's raised to the power. So there's a trick here. Now, you could say, hey, I don't like tricks. I'm just going to do this by looking up an integral table. If that's what you need to do, do that. But I'm not going to do that. I'm going to do it the long way. And so that means I need to start a new sheet of paper. So let's write up here where we have I equals 2 pi rho double integral r to the fourth sine cubed theta d theta dr. I switched the order up just for fun. So I need to do something that I can do here. And the trick is to know that if I take the derivative of sine theta, then, or if I take the derivative of cosine theta, I would get sine theta, negative sine theta d theta. So I'm actually going to write this sine theta instead of sine cubed theta. I'm going to write that as sine squared theta times sine theta d theta. Sine d theta. So I just broke that into two pieces. Now I can write sine squared theta is equal to 1 minus cosine squared theta. Do you like that? So we know that cosine squared plus sine squared is 1, so I can write sine squared as this. Now I'm going to say u equals cosine theta. If I do that, I can take the derivative du, and I'm going to get negative sine theta d theta. And you'll notice here that I have that term right there with a negative sign. So if I replace this, I get, let's write the whole integral, 2 pi rho double integral r to the fourth 1 minus u squared, and then I have this is minus u, so I just get a minus sign out there, and then I get du. Now, and then I have the dr. Now that integral I can do. I can integrate 1 du and negative u squared du. So let's do that. I'm not going to change the limits because I'm going to change it back to phi theta before I evaluate it. So I'm going to get I equals, and this is where you make a mistake, so let's be careful here, 2 pi rho. I'm going to, and then have r to the fourth dr. Let's put that together. Now if I integrate 1 du, I'm going to get u. And then the integral of negative u squared is going to be negative u cubed over 3. And then I need to evaluate that from theta equals 0 to pi. Okay, let me just check my notes because I'm super afraid I'm going to make a mistake. Okay, I think we're okay. Okay, I'm going to proceed. So now I'm going to put back in my u because my limits are in theta. So this is going to be equal to negative 2 pi rho, the integral over r to the fourth dr, and then I get cosine theta minus cosine cubed theta over 3 from theta equals 0 to pi. Okay, so I guess we just start plugging stuff in, right? Because I need to do it at pi and then at 0. So I'm going to put negative 2 pi rho, the integral over r to the 4th dr. I'm trying to be very careful here because I know that I'm going to make a mistake. So I'm going to put in cosine theta at pi. Cosine theta of pi is negative 1, right? Yeah, negative 1. Cosine of pi is negative 1 cubed is still negative 1. So I'm going to get plus 1/3. And then I'm going to get minus, I'm going to put in this cosine of 0 is 1. And then this is going to be also 1 minus 1/3 in parentheses. I know that's messy. It's not messy. It's just confusing. Okay, so but now I can do this. Negative 2 pi rho r to the 4th dr. I have negative 1 minus 1, so it's going to be negative 2. I almost put 1. Okay, and then I can get 1/3 plus 1/3, right? Because that's a minus, so it's going to be plus 2/3. I feel like this is the moment of truth, or I'm going to make a mistake. I feel like I'm making a mistake here. Okay, so this is going to be equal to, if I get a common denominator, this is going to be 6/3, negative 6/3. So it's going to be negative 4/3. So I pull that out front, and I get 8/3 pi rho r to the 4th dr. I'm checking because that's what I got before. Okay. Yes. Whew. Okay. We're almost done. Now I got this easy integral right here. I can integrate that, and that's going to be r to the 5th. So now I'll get I. Oh, there. The negative canceled. I is 8/3 pi rho. If I integrate this, it's going to be r to the 5th over 5 from 0 to r. And if I plug that in, I'm getting a new sheet because I feel pressed. So I say I is 8/3 pi rho r to the 5th over 5, 0 to r. Okay. And so that's just going to be equal to 8/3 pi rho over 5 r to the 5th. Now I can use my density. Remember, density is m over 4/3 pi r cubed. If I put that in, I get I equals 8/3 pi m r to the 5th over 4/3 pi r cubed. So this 3 cancels. Wait, where'd my 5 go? And 5. That cancels that, and I get 2. Cancel, 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 cancel. 2/5 m r squared. Did it. Whew. That's not easy. Okay. Let's do it in Python. So if you don't care about Python, you don't like fun stuff, then that's it. Just take it off. Okay? Close. But if you want to see something cool, maybe you don't even think this is cool. I think it's cool. So the basic idea in a Monte Carlo calculation is I'm going to take a sphere, and I'm going to break it into n number of points. Let's say it's 100 points. They're just randomly distributed over this. And then I can say I is the summation over I, mi squared, where that's the distance from the thing. So I'm going to make a bunch of points in a sphere, and then I'm going to just add up all the points. And they're going to be randomly distributed, so it'll be uniform. One of the things is the mass of each of these points, dm, I'll call it dm, is going to be the total mass m over the total number. And I need a number for both m and r. And let's just pick those as different. Let's pick m is 2 and r is 1. And then that way we can calculate and compare with this calculation right there. So let's jump over to Python. I will give you this code. And again, if you don't want to see this, look away. Just look away. Are you still looking? I assume you want to see this. Okay, I want to see it because it's fun. Let's just put in our stuff. So I'm going to say m equals 2, r equals 1, n equals 0, n equals 100. So n equals 0 is my counter. I want to count up to 100. And there are different ways of doing this, and I'm not using real Python. This is WebVPython, so it's a little bit different, especially with random numbers. So let me just show you how to count. So I'm going to say while n is less than n, print n, oh no, lowercase n, and then n equals n plus 1. I'm going to run that. And so there I got 100 points. So that's how we count. But I don't want to count. I want to make the stuff. So let's see. Oh, I need here dm equals m over n. So let's make a random point between -1 and 1. I can't make it in a sphere. I can make it in a box. So I want to make a box. So let's make a random vector. I'm going to call it RT. It's going to be R times vector random. So random returns a number between 0 and 1. But I want between -1 and a 1. So I'm going to say 2 times random minus 1. That's my x coordinate. And then my y coordinate, it's going to be the same thing, a different random number. And my z coordinate is a different random number. So I'm generating random numbers between -1 and 1. And then I'm going to put a sphere there. I'm just going to say sphere position equals RT. And the radius, let's say, is r over 40. I'm just picking a number. And let's just see what happens here. There. So I have 100 random points in a cube. If I can do 100, I can do 1,000, right? And there's 1,000 points in a cube. Okay. So now I don't want a cube, I want a sphere. So I can get a sphere by cutting away anything that's not in the sphere. So I have a cube. Now I just cut away unsphere things. So let's do this. If mag RT is less than or equal to R. So mag returns the magnitude of that vector. And so if the magnitude of that vector is in the sphere, I'm going to keep it. If not, I don't care. I'm just going to move on. So I'm going to make the sphere and count, add it as 1,000 points, only if it's in the sphere. So if I run that, I get 1,000 point sphere. Isn't that lovely? It is lovely. Okay, now I want to calculate the moment of inertia. So in order to do that, I'm going to add go through and add the dmr squared to each time I make a point. But I need to add it to something. So I need to start with a value, I equals 0. Now I'm going to add I equals I plus the mass of that piece, and it's r squared, but r with respect to the z-axis. So it's going to be its x value squared plus its y value squared. Square rooted, then squared. So, but I just don't worry about the z value. So this is going to be dm times rt dot x squared plus rt dot y squared. So rt dot x is the x component of that vector. Rt dot y is the y component of that vector. I don't care about the z. And that's it. So then down here, I'm going to say print I equals I. And the units would be kilogram meters squared. And then let's print out I theory, IT. It's going to be 2/5 times m times r squared. And let's print that. Print IT equals IT kilogram meters squared. And let's see what we get. So we don't get the same thing, because I only used 1,000 points. I didn't use an infinite number of points. But it's pretty close. And every time I run it, I'll get a different answer because it's random. So it's pretty close. And if I do, let's say, 2,000 points, that's going to be better. If I do 3,000 points, it's going to be even better. Well, that one actually not. If I do 4,000, let's do 10,000 points, but no, because it's going to get bogged down. I'm not going to draw the spheres. I don't have to draw the spheres, but I can do 10,000 points and I get a very good answer. And that's the idea behind a numerical Monte Carlo calculation, is to use random numbers to calculate this, which is a little bit easier than integrating, but you don't get an exact answer. So I hope that's just fun, a fun bonus thing for finding the moment of inertia of a sphere. I'll put a link to this code down below.